These are the three notes on rate of change and slope. So we are going to find the rate of change between 2 points. It may be linear or not. And then we're going to find the slope of linear functions. So to start off with, we need to define these things. Rate of change is a ratio. So rate is a ratio that describes how much one quantity changes with respect to the change in another quantity. So it's a rate. It's how fast it's changing, comparing two different rates. And so in the coordinate system and in math, we're talking about the change in the y values over the change in the x values. In science, a lot of times we'll use this little letter called delta, and that's just a triangle. It's a Greek alphabet. Change in y over the change in x. So how much are my y values changing? How much are my x values changing? And it's always the y value over the x value. That's an important part to understand. Now, if the rate of change is constant, that means that it's the same for any pair of points on the graph of the function. So if it has a constant rate of change, that means maybe my y value changes 3 every time my x value changes 1. Or every time my y value decreases by 2, my x value increases by 5 over and over again. No matter what point you start at, that's the same thing. That's constant. Lines have a constant rate of change, and we call this constant rate of change slope. So these things get interchanged quite a bit. Slope has to be constant. And so what will happen is every point, the rate of change will be the same. That I will go up so many units and over so many units, up so many units and over so many units, the same amount. Or from this point, I can say up and over, up and over. It's consistently climbing a nice staircase, even staircase. Whereas rate of change could be like your temperature of somebody that's sick. So maybe as a normal, it's 98.6. Then we get a fever, and then maybe the next time we take it, the fever's still there. And then maybe we take some medicine, and so it drops down. Then maybe it spikes again. And so this is not a linear function. This is all over the place. So what we can do is we can measure from one point to the next. So maybe I can measure from this point to this point what my rate of change was, or from this point here to this point here what my rate of change was, but they're not consistent. They're all over the place. So that's just rate of change, how much it changed. But a constant rate of change is always the same amount over and over and over again. So use the table to find the rate of change, explain the meaning of the rate of change. We have to look. We don't know if it's constant or not. So what we can do is we use a calculator if you need to, and we just simply calculate the difference between these points. So these points are increasing. So as this value here is increasing, it's easier though to start with the 152 and subtract the 76, and that's a change of 76 units. So in this case, it would be distance traveled 76 miles. So my miles increased, it went up by 76, and then it went up, if I take the 228 and subtract the 152, it went up again 76 miles. So my y value, the change in my y was consistent. And then if I look at my x values, between 2 and 4, that increased by 2 hours. And then from 4 to 6 is 2 hours. So it also increased each time consistently. So my rate of change here is the change in y, which is a positive 76. It increased by 76. And then my change in x was 2. So 76 miles every 2 hours. And actually we can simplify that because 2 goes into 76. That's 38 miles per every hour. And so that's what it explained the meaning of this rate of change. This person is traveling at 38 miles per hour between these different driving distances. Now, if you look at this travel, really helps to understand what we're talking about by reading the title. So we're talking about the passports that were issued in the United States. On the bottom, we have the years that they were issued, and on the left-hand side, we have the number of millions of passports that were issued in those years. If you look at the graph, it is not constant because I can see different steepness of my lines. So between 2002 and 2004, there's an actual rate of change, and then it changes, and the line gets a little bit steeper. And so from 2004 to 2006, the amount of passports increased slightly. Not a lot, but it's still rising faster, so it has a steeper rate of change. So they want us to find the rate of change between 2002 and 2004. So I'm going to put that in red because I highlighted that in red. So if I look at that, I need some ordered pairs. And so my ordered pairs would be my time, 2002 with 7 was my first ordered pair, and then 2004 and 8.9. Now I wrote them as ordered pairs. We could also put them in a table of values like we had in the last example. But the change in my y values, my y value, if I subtract those two, went up. So if I take 8.9 and subtract 7, it went up 1.9 million passports. It's positive because it went up. And then my time, I can just do that quick math, 2 years. So this increased 1.9 million passports every 2 years. Since we want to get a rate, anytime we do a rate, we want to actually divide that out. So 1.9 divided by 2, that's 0.95 million, just under a million per year. 0.95, almost 1 million every year. Then they asked us, so this was between 2002 and 2004, then they asked us the same information from 04 to 06. So if I did that in green, 2004 to 2006, I could look at that in a table format just to be different. So 04 was 8.9 and 06 was 12.1. So you don't have to do the table, you can do it right from the graph. You could use ordered pairs. So now I can see in my table of values, the rate of change increased again. So it's going to be a positive number. So I'm going to subtract 12.1 and 8.9, and I get a difference of 3.2. So that's the passports. And then again, my time increased by 2 years. So 3.2 million passports every 2 years. When I divide that out, because that really doesn't make sense to me, but when I divide out my rate of change, 3.2 divided by 2, that's an average of 1.6 million passports per year. And so you can see the difference. We were just under a million in the first 2 years, and then we are increasing by almost 1.5 million in the last 2 years. And so that's why that slope is a little bit heavier. Determine whether the function is linear. Well, we said if it's linear, it has to have a constant rate of change. So I'm going to quickly go through this and just show with the table of values that things are constant or not. So my y value went up by 4. From 16 to 20, we went up by 4. And from 20 to 24, we went up by 4. So my y values were constant. We just got to make sure that the x values are also constant. And so my x value went up by 3. Then it went up by 6, and then it went up by 3 again. So because my x values and my y values are not all constant, this is not a constant rate of change. Because my first rate of change was 4/3, then my next rate of change were 4/6, and then 4/3 again. And so because it wasn't constant here, we can say not linear. So the next one, if I look at my next example, my change in y increased by 2, increased by 2, increased by 2. And my change in x, I went from 5 to 10, that's an increase of 5. 10 to 15, increase of 5. And 15 to 20 is an increase of 5. So they were all consistently 2/5. So that would be my slope. For every 2 that I go up, I'm going 5 over. So yes, linear. And the last example here, my y value went from 5 to 1, so it went down by 4. from 1 to negative 4 is really, hold on, negative 4 plus 1. I can't get that to go. That's actually a change of 5. That went down 5 units. So if I'm at 1, to go to 0, that's 1 unit, and then 4 more. That's a change in 5. And so right there, I can tell we're not linear. And then the negative 4 to the negative 10 is down 6. We should really, though, put them as fractions because they could simplify to be the same thing. So let's look at our change in x, because our x values could be all over the place too. So from negative 10 to negative 2, that's actually an increase of positive 8. From negative 2 to positive 6, that's an increase of positive 8, and then a positive 8 here. So even though the change in my x values was consistent, negative 4 over 8 is not the same thing as negative 5 over 8, which is not the same thing as negative 6 over 8. So when I'm taking the change of the y's and putting them over the change of the x's, they are not equivalent ratios. So not linear. Okay, so when it's a line and it's a constant rate of change, we said that that's slope. We actually have a nice little formula for slope. So it's the greater the slope, the steeper the line. That's what that means. Slope measures the steepness of the line. You can use any 2 points in any order to find slope. A positive slope for your y is telling it to go up that many, and a positive value for the x is telling it to go to the right. Negative would be your down and to your left, just like the coordinate plane. And so slope, let me just give you the slope formula, sorry. So slope is actually the formula. We use little m for slope, and the little m is taking the change in y value. So what we did in the tables, what we did from the graphs is we took the 2 y values. So I can say y2 minus y1, and then put that over the change in x. So that would be x2 subtract x1. Now you can put the second coordinate first. I'm going to actually give you another formula that just says if you take the first order pair of y and subtract the second y, you just got to make sure that you're consistent and use the first x value before you use the second x value. So those little numbers that are down below, those are called subscript. They're just to label that the 2's are telling you it's from the second order pair and the 1's are telling you it's from the first order pair. So if you look what I did there, if I pick the second order pair first on top, I have to pick the second x value on the bottom first. If I pick the first y value to be on top first, then you have to pick from that x value first on the bottom. Otherwise, it messes it all up. So let's go ahead and try this formula. So no story, but it's a constant rate of change. I don't have any graph. I can just use the formula. So my formula, basically how I memorize the formula, is just change in y over the change in x. I get rid of the 1's and 2's. It doesn't really matter as long as you're consistent. It does help if you label your ordered pairs x and y, because it gets confusing. A lot of people want to put x first on top. A lot of times we mess up the order, so just be careful. So I'm looking at this. I need to subtract the 5's and the 2's, and then the 5's and the 3's. So on top, I'm going to do 5 minus 2, just because I want my top number to be nice and pretty. So 5 minus 2 on top. Once I commit to doing 5 first on top, I have to put the 5 on the bottom first. And 5 minus a negative 3. Well, when you subtract a negative 3, it's really like adding it. 5 minus negative 3 becomes plus positive. So what I have here is 5 minus 2 is 3, and 5 plus 3 is 8. So my slope is 3/8. What that means is this line rises 3. It goes 3 up to every 8 that it goes to the right. Because they're both positive, it'd be going up 3 over 8 to the right, up 3 over 8 to the right. If I wanted to, I could change that. We always want to keep our slope as positives, but if I was going to graph, I could graph the opposite. So I could say I'm going down 3. But if I change the direction of the top, I have to also be consistent and change the direction on the bottom. So if I was to graph from one to the next, I'd have to go down 3 and 8 to the left. So those two slopes are the same, but the best one is where the slope is in simplest form and positive if it's supposed to be positive. For number 7 here, finding the slope, again, I'm going to label x and y, x and y. All right, draw your arrows. I'm going to subtract the 4's, and then I'm going to subtract my x's here. So slope is equal to y minus y over x minus x. I'm going to do 4 minus 4. I worked with the first 4. So since I use this 4 first, I'm going to use this 4 on the bottom first. So 4 take away a negative 2. Again, when you subtract a negative 2, it's nice because you get to add them actually. 4 minus 4 is 0, and then 4 plus 2 is 6. 0 divided by 6 is 0. Slope is kind of like, we're just simplifying fractions, so it just does fit to go across the page rather than down. It's one of the only times I will say that in algebra. So this is a 0 slope. And a 0 slope is saying I'm going 0 up or down, and I'm running 6 to the right. And what that is, those two ordered pairs, if you were to graph them, 4, 4, and negative 2, 4, they line up horizontally. Horizontal lines only run. They only run sideways. So they have a 0 slope. They don't go up any. They're just 0. They're flat. All right. So I'm going to skip these two because I think we've done that quite a bit now. And so I'm going to go on to the next one and just talk about a summary. So positive slope always has to rise to the right. It's going up. Negative slope falls to the right. So when we read these graphs from left to right, you should be able to check, is my graph a positive slope? It should be rising, going up. Negative slope, going down. Slope of 0 is horizontal, undefined, and then undefined slope is vertical. Okay, so a horizontal line only runs, okay, with 0 rise. We're talking about rise over run. Sorry about that. And then a vertical line only rises. So it only rises, and it has 0 run. So what happens when you find an undefined slope is you'll have like 3 divided by 0 or negative 5 divided by 0. You cannot divide by 0 in math. That is an undefined thing. Your calculator will yell at you if you try to do it in undefined slope. All right, these last two problems involve solving for an unknown value. So they're giving us slope. They're giving us the slope is negative 5/8. So that's what your m value is. M is negative 5/8. So if you set up your slope formula, here's my x and y, here's my x and y, and you use your slope formula, y minus y over x minus x, you just want to replace the m value. You have the m value, negative 5/8. And then you replace everything you know, but we don't know this x value. So I like to keep my variable positive. So I want that x value to show up first on the bottom. So when I subtract, I'm going to subtract 4, take away a negative 1 on top. 4 minus negative 1. And then the bottom, I'm going to do the p minus the 3. Okay, so the 4 minus a negative 1, change sign and add. I'm going to work down the page here. I got an equation. So negative 5/8 is equal to 5 over p minus 3. I'm going to put that in parentheses because that's one number. And if you remember from chapter 2, this is called a proportion. When you have a fraction equal to a fraction, we can do the cross products. So I'm going to do a cross multiplication of these two numbers right here. So I'm going to do negative 5 times the quantity, p minus 3, is equivalent to 8 times 5. On the left-hand side, I have to distribute. Negative 5 times p is negative 5p. And then negative 5 times negative 3 is a positive 15, is equal to 40. And then just solve. Subtract 15 from both sides. Negative 5p is equal to 25. Divide by negative 5, divide by negative 5. P is equal to -5. So what we were looking for was the x-coordinate of this other point. If I had a -5/8 slope, that point must have been -5. I know I have another one of these in here. I'm going to skip over this one just because of time, and we're going to get on to the lesson summary and the practice problem. Good luck.